For decades, the Philippines was plagued by problems of overpopulation.
The more people we had, the more resources we had to allocate, and we had scarce resources.
But the country has turned a corner. In 2022, the number of births per woman fell below 2 for the first time in 7 decades.
This assignment focuses on the application of first-order differential equations to analyze the population data of the Philippines from the year 2004 to 2024, with the aim of achieving several key objectives. These include applying the Malthusian model to determine the population at any given year, predicting future population trends beyond 2024, and estimating population values prior to 2004. In addition, this assignment also aims to examine and explain the differences between the model's results and the actual recorded population data.
Moving on to the core of our assignment, this is the data table representing the population growth over a 20-year period, spanning from 2004 to 2024. This dataset serves as the primary foundation for our mathematical modeling and subsequent calculations. If we look at the initial data point in 2004, the population stood at approximately 86.4 million. By the end of the first decade in 2013, it had surpassed the 100 million mark. Fast forward to the present year, 2024, the population has reached an estimate 115.8 million. The most notable observation from this table is the consistent and steady upward trend. Over these 2 decades, we can see a total increase of roughly 29.4 million people. The growth does not show any drastic fluctuations, suggesting a stable and predictable growth rate, which is a crucial factor for the accuracy of the mathematical model we have applied. However, to visualize the trajectory of this growth and to perform a deeper analysis, we have translated these raw figures into a graphical representation. I will now hand it over to my teammate to explain the graphical presentation and interpretation.
Well, so now I'm going to present the application of first order differential equation to model population growth. I'm going to talk about the calculation how to find the first order differential. So we utilize the growth equation dp over dt equals to kp, which leads to the general solution p equals to ae power of kt. So, our objective is to determine the particular solution by identifying the specific constants A and K based on the provided data set for the Philippines. To find our constants, we define our initial condition at t equals to 0 corresponding to the year 2004. At this point, P equals to 86,394,504. By substituting this into the general equation, we find that our initial value constant A is exactly 86,394,504. So next, we solved for the growth constant K. Using the data point for t equals to 1, the year of 2005, we set up the equation 88,015,962 equals to 86,394,504 e power of k times with 1. By dividing the populations and taking the natural logarithm of both sides to isolate k, we get an approximate value of 0.0186. This gives us our finalized mathematical model Pt equals to 86,394,504 e power of 0.0186 t. With the particular solution defined earlier, we can evaluate the function at different intervals of t. First, we calculate the future value where t equals to 22, substituting this into our model. So P20 equals to 86,394,504 e power of 0.0186 t. So we substitute the value of 22 for t. This yields a result of approximately 130,076,000 672.2 in the year of 2026. We then perform a backwards projection for t equals to -10, representing the year of 1994. So 86,394,504 e power of 0.0186t. So we substitute the t with -10. The calculation results in approximately 71,731,075. These values demonstrate the exponential nature of the function over a 32-year span.
Moving on to the graph segment, we have plotted the population growth of the Philippines from 2004 to 2024. As you can see, the data follows a clear linear trend. By applying a line of best fit, we can determine the rate of change or the gradient, which tells us how many people are added to the population annually. We notice a strong positive correlation starting from 85 million in 2004 and steadily climbs toward 115 million mark by 2024. This linear model allows us to make future predictions such as estimating when the population may hit the 120 million milestone.
So, for analysis, the values from the particular solution is consistent with the actual values. However, the values are not an exact one-to-one. There is a slight difference from the particular solutions and the actual values. For example, when we use the year 2024 to calculate the differences between the two, the t is equals to 20. When we substitute the value into the particular solution formula, we got the value of 125,326,711, whilst the actual value of year 2024 from the table population of growth in Philippines is 115,843,670. So to calculate this percentage error, we use the formula of actual value minus calculated value over actual value times 100%. And we got the percentage error of 8.19%. For discussion, the particular solution for our differential equation predicts a population of 125.3 million by 2024, but the actual data shows only 115.8 million. This difference of nearly 10 million people occur because our mathematical model assumes a constant growth rate and unlimited resources. In reality, population growth in the Philippines has slowed down due to several socio-economic factors. Over the past 20 years, improved family planning and higher education levels have led to smaller family sizes. Additionally, migration and the impact of the COVID-19 pandemic caused the actual growth to stay below our exponential prediction. In the future, as more people move to cities and the population ages, we expect the growth rate to continue decreasing. Instead of a J curve that shoots up forever, the population will likely follow an S curve as it reaches its natural limits.
In conclusion, our study demonstrates that while the differential equation for growth provides a strong foundational model for predicting population trends, it cannot account for the complex socio-economic variables of the real world. The 8.19 percentage error we calculated reflects a transition from theoretical exponential growth to a more realistic logistic growth pattern. Factors such as improved family planning, migration, and global health events have successfully slowed the growth rate below our initial mathematical predictions. Ultimately, as the Philippines continues to develop and urbanize, the population is expected to reach a carrying capacity where resources and growth reach a sustainable balance. This project highlights that while calculus is a powerful tool for forecasting, it must be paired with an understanding of the human and environmental limits to be truly accurate.